Hello, this is the video for the second Stata session that we had. So in this session, we're going to be estimating demand functions. We're estimating demand for fizzy drinks. And we have a sample of 3,000 UK households from 2009 and some information about their consumption of fizzy drinks and the market conditions that prevail for that level of consumption. So first thing you want to do is open up Stata. It might look a little bit different than this. This is for a Mac if you have a PC, but it'll be largely the same. And then we want to find the data. So we just go here and open up the data. And we're looking for the data set called fizzy drinks. This is available on the Blackboard. So if you don't have it, you should be able to see it there. Once you've done that, if this line of code is black, it means Stata's recognized it and executed the command. And you can look over here in the variable window, and the variable window will tell you which variables you have loaded into your Stata. So the first thing you want to do whenever you have a data set, whenever you're starting a new project, whatever it is, whether it's your first year project for applied economics or your PhD dissertation or your Nobel Prize winning paper, you always want to just get familiar with the data. Just really have a good understanding of what it is you have, what the characteristics of the variables are, what things you might need to be watching out for. You can even just open it up and have a look at the data set, right? And just see what's going on. Is there anything that looks funny, maybe? An easier way to do that is to use describe and summarize. So describe, the first command will just tell us what is actually in our data set. All right, so here we have the name that Stata uses. This is technical information, and this is sort of the human language, what each variable is. So the HHNO, which doesn't mean anything to you and me, is the household identifier. But the HHNO will mean something to Stata. So if you want to tell Stata to do something with this variable, you have to use this name. Okay. Next thing we can do is summarize. Sorry, that's an American way. So here we see a brief summary of the distribution of each variable. So we have the number of observations, we have 3,000 for each. We have the mean, we have the standard deviation, the minimum, and the maximum. Okay? So you kind of want to look at all that and start to understand what's going on, what do the variables look like, is there anything I need to be aware of. Now, the first thing we want to do is, in terms of estimation, is we're going to estimate a simple log-log model of demand for fizzy drinks. So here we have the quantity of fizzy drinks, we have the price faced by each household for their fizzy drinks. We have a variable here, and what kind of variable is this? It's a dummy variable, right? 0 and 1. That's equal to 1 if this household is a big consumer of fizzy drinks, if they consume a lot of fizzy drinks. Inc is the income, num adds is the number of adults in the household, num child is the number of children, and p other or pother is the price of other soft drinks, okay, other than fizzy drinks. If we want to estimate a log-log model, if you look at the problem set, number 2 is written out the model that we want to estimate. And the first thing we need to do then is take the log of each variable. So you can do that using this command. You can use gen or generate. Right? Gen is just the short version of it. Stata recognizes some abbreviations. Generate a new variable called lnq that is equal to the log of quantity, which is the level variable that's already in our data set. All right? So we just hit enter. You'll see it's black, so Stata executed it. And if you go up here and look in the variables windows, you'll notice that there's a new variable that showed up, lnq, meaning that Stata has now added this variable to our data set. That's a function of the quantity. It's just a log of it. So we can go ahead and do this for all the other ones: log income, log price, log number of adults, log number of children, and log other. So I've already written up some code here. I'm just going to run it like this. So generate log lni is the log of income, generate lnp is the log of price, generate lna is the log number of adults, generate lnc is the log number of children. Now have a look at this right here. This will come up in a second. It says 1,675 missing values generated. You pay attention to that. Stata always tells you what's going on with the data, and you need to always pay attention to what's going on. And LNO is the log of the price of others, and you'll see in this window, in our variable window, we've added all those variables. So now we can go ahead and run our regression. So you can type reg ln q, ln p, ln I, ln a, ln c, ln o. So that's our model. We're saying Stata regress using ordinary least squares. Regress the log of the quantity on the log of the price, the log of the income, the log number of adults, the log number of children, and the log price of other soft drinks. We hit enter and we get these results. Here we have our price elasticity. So remember, this is a log-log model. So the coefficients are betas. This is just our betas here. Our betas are interpreted as elasticities. We have our standard errors, our t-scores, our p-values, and our confidence intervals. So you should be able to interpret these coefficients by now, and you should be able to understand whether or not these are statistically significant or not. All right? So our price elasticity is negative 1.12. So it looks like it's probably price elastic, meaning that the 1% change in price will lead to a greater than 1% change in the quantity demanded. Now, as we're looking at this policy of adding, say, VAT to fizzy drinks to try to reduce how many fizzy drinks people are drinking, that's what's in the problem set. What we want is a big number for that. We want people to be really sensitive to changes in the price. That means we can add a little bit of VAT to fizzy drinks and people's consumption will fall by a lot. So we always, we would want that to be bigger than 1, really. And it looks like it is, just judging from this estimate. And it's statistically significant, right? T-statistic bigger than 2. P-value smaller than 0.05, and the confidence interval does not include 0. Now, something that should stand out when you're looking at this, and you always want to consider all the information the Stata gives you. We have our R squared, okay, that's fine. But this is the problem here. Number of observations equals 1,325. We already saw in our summary, you can still see it up here. The number of observations that we have in our data set are 3,000. So something's happening, something's gone wrong. That is, Stata's not using all the information available to it. Right? And the reason that it's doing that is because of this right here. That is, when we logged the number of children, we get a bunch of missing values. And the question would be, well, why is that happening? Well, let's go ahead and summarize the number of children again, just to have a look at that variable. So you can do sum num child. All right, well, there's 3,000 num childs, right? There's 3,000 observations for num child. Mean, okay, there's a 0. So what is the log of 0? The log of 0 is undefined. It doesn't exist. Meaning, if we take the log of 0, we don't get any information. And in fact, if you go and look here at our data set, if you look, here we have log, this is the variable. So here we have number of children, 0, 0, 0, 0, 2, 2, 1, 0, 0. Here we have the log of that variable, and all the zeros are turned into missing values. And if there's a missing value, it doesn't matter that we have all this information for the observation. So this is observation number 1. Even though we have information for everything else, that is, we have a valid value for the variable, if one of them is missing, Stata throws away that observation and can't use it. So we need to find another way to address this problem, and there's a couple options. So the reason we're including this, right, we're including number of adults and number of children, because households with more people are probably going to consume more fizzy drinks, everything else being equal. They just have more people, so they drink more. So we want to control for that when we're trying to estimate this price and income effects. We want to control for the number of people in the household. Well, the first way we tried it is to take the log of number of adults and log of number of children. And that didn't work because log of children that are 0 is undefined, Stata drops it. So how else could we control for the number of people in the household? Well, we could create a dummy variable that's equal to 1 if there's any children in the household. Maybe we don't care if there's 2 children or 1 child or 4 children. We just care if there's any children. So we could create a dummy that's equal to 1 and 0 because we never take the log of a dummy. Okay? We could create another variable that's just the number of people in the household. So the sum of the number of adults and the number of children. And then that would never be equal to 0 because there's always at least 1 adult. Another option we could do is to take the number of people in the household and then look at the quantity of fizzy drink per person consumed and the income per person in the household. Then we have common units across on either side of the equation. And that's actually the approach that we're going to be using. Now, those other approaches are perfectly valid. A fourth approach could even be, well, let's not take the log number of children. Let's just have it be linear. We're not so interested in estimating this coefficient as an elasticity. We're just interested in controlling for it. So that would be the simplest way to do it, is just to lop in level number. So just use the variable num child instead of log LNC. So all of those are valid. This is what when we talk about functional form, there's lots of different ways that you can control for these different things. And it's just about which one you think is the best way to do it for you, and each data set and each question will have slightly different variations for what you think might be best. And in this case, I've just chosen, we're going to just look at quantity per capita within the household and income per capita. So the first thing we need to do is generate a new variable called, let's just call it people, you can call it whatever you want, which equals num child plus num adds. So we're saying create a new variable called people, which is just equal to the sum of the number of children and the number of adults. Okay. Now we're going to generate a new variable called inc per capita, which is equal to inc divided by people. So that's the amount of income in the household per person. Okay, because households with 2 adults will have more income than a household with 1 adult. Right? And we want to generate QPC, so the quantity per capita, is equal to quantity divided by people. And now we're going to take the log of each one of those. We'll have log income per capita and log quantity per capita. Okay. So we'll generate ln inc pc equal to that. And we will QPC equals ln QPC. Great. Now we can re-estimate our model, and if you don't want to type the whole thing out, we can just go up here. We'll modify this by saying that's quantity PC and income per capita, and then we can delete the log number of children, log number of adults, and oh. There we go. So here, we're back. We have all 3,000 observations that we're using. All right? And we can look at our results. So one thing to notice, well, our price elasticity came down a bit. So this suggests our price elasticity may be sensitive to the functional form, but it may have just been sensitive to the fact that this sample of people don't have children, or this sample of people all have children. So maybe households with children are more price sensitive than households that don't have children. That could be an interesting research question, right? So now we're looking at the full sample. We don't really trust, so these results up here, we can't overly trust these because this is a selected sample. What we want is a representative sample. So we go back down here, we're using all 3,000 observations. We find a price elasticity very close to 1, an income elasticity that's 0.24, so this is a normal good, right? Bigger than 0. And the price elasticity with respect to the price of other drinks is positive, meaning what? What kind of goods are these? If the cross-price elasticity is positive, meaning if the price of other soft drinks goes up, demand for fizzy drinks goes up. So have a think about that. Okay. Now, what we've done here, implicit in this sort of modeling, is that the average price effect is applicable for the entire population. That is, on average, for everybody in the population, the price sensitivity will be equal to this. The price elasticity will be equal to 0.99, basically 1, almost exactly 1. Okay? But that might not necessarily be the case. There's lots of reasons why one group might have a different price elasticity than another group. And in fact, if you remember learning about price discrimination, the whole idea of price discrimination rests on the idea that different groups of people have different price sensitivities. So we might want to try to pick that out. And if we think about our policy, well, what is the aim of our policy? The aim of our policy is to reduce obesity, because reduce consumption of fizzy drinks that's leading to obesity. But someone that has a Coca-Cola once in a while, it's probably not leading them to be overly obese. Someone who drinks Coca-Cola for breakfast every day, they might be having a problem. And it's those people that we really want to target. So what we're really interested in here is, well, how sensitive are people that consume a lot of fizzy drinks? Because those are the people that we really need to see a reduction in their consumption. And to do that, we're going to use something called an interaction term. So if you remember in the last data session, we had dummies that allowed for an intercept shift. Well, now we're going to allow not only for an intercept shift, but also for the slope coefficient to vary across different groups. So first thing we want to do, actually this is probably about the 10th thing that we want to do, but we want to generate a new variable that's equal to the interaction, so the product of our dummy big, which is 1 for people that consume large amounts of fizzy drinks, and the price. Now, what we could do here is have a look at, let's say, summarize. So you can just say sum quantity if big equals 1. So you need double equal here. It's just Stata syntax. All right. And then let's say if big equals 0. So we can see, look, people that, households that are big consumers. So when big equals 1, the average consumption is 2.79 liters. And if you're not a big consumer, the average consumption is 1.94. Okay? The maxes are the same, actually. So, but on average, we have this one down here. Okay? So now we want to generate this new variable. Generate, and let's call this inter for interaction. Okay? You can call it LNP big, you can call it whatever you want. But we'll call it inter for interaction. And this is going to equal big times, use the star symbol, the asterisk, times LNP. Now we have a new variable over here in the window, inter's right there. Now we're going to re-estimate our model, but we're going to include the dummy variable big, so this would just allow the intercept shift, but would make sure would hold the price elasticity to be constant across different groups on average. And the interaction term, and we re-estimate the model. So let's have a look at what we have here. We have a price elasticity that's very close to 1. We have an income elasticity that's unchanged from the previous model, about 0.24. The cross price elasticity is unchanged, not 0.35. But we've added these two variables. The coefficient on big, which is a dummy variable, is equal to 0.3. So how do we interpret that? Well, it's an intercept shift. So what this would tell us is, on average, in ceteris paribus, people that are big consumers of fizzy drinks consume 30% more than people that are non-big drinkers, non-big consumers. Okay, that's the way that we interpret that coefficient. Now, this is the interesting one, the interaction term. It's statistically significant, as is everything else. And we need to think about this in terms of taking the first derivative of our dependent variable with respect to price. Okay, so just think about your calculus and maybe just write it out as an equation and think about taking the first derivative of our dependent variable with respect to this variable, log price. Okay? So if we don't have this interaction term, that derivative is just going to be the beta, the coefficient, which is this. But we do have this. So there's some groups for which big is equal to 0. If big is equal to 0, the people that are not big consumers of fizzy drinks, then the interaction term is also 0. Because look at our definition of the interaction term, it's just the product of the two. So for people who are not big consumers of fizzy drinks, the price elasticity is equal to the coefficient on the log price. That is the price elasticity of fizzy drink consumption for people that are not big consumers of fizzy drinks. Now, for that group of people, big consumers of fizzy drinks, big, BIG, is equal to 1, which means this variable is still in the equation. And the first derivative of our dependent variable with respect to the log of price will have this plus this. All right? It's the sum of the two coefficients. So we have one price elasticity for people that are small consumers of fizzy drinks, which is 0.99, and we have a second price elasticity from within the same model that is the price elasticity of consumption of fizzy drinks for people that are big consumers of fizzy drinks. And the sum of these two is going to be what? About 0.77, right? Because this is negative, this is positive, right? So what that's telling us is that families that are big consumers of fizzy drinks are less price sensitive. Their price elasticity is smaller in absolute value than people that are not big consumers of fizzy drinks. So the families that we're really targeting with this policy, the people that we want to be very responsive to changes in the price by adding VAT to it, changes in the price of fizzy drinks, are actually not as sensitive as the population as a whole. And so this has welfare implications as well. If the government did this, I, as the average consumer of fizzy drinks, will buy less of it because the price will be higher. So I'm worse off necessarily. And the people that it's trying to force into better behavior, push them towards not drinking as many fizzy drinks. Force is probably too strong a word, but push them in that direction by increasing the price. It's not having as big effect on them. They continue drinking fizzy drinks less than they were before, but I'm drinking a lot more less than I was before. They're drinking a bit less than they were before. Okay, so these interaction terms are really important and can reveal really interesting things about what's going on in these demand functions. That a demand function isn't, very rarely is it ever so simple as quantity regress on price and income. Because those price and income effects can vary over the characteristics of the people in the sample in very interesting ways, as this example shows. All right, I hope that's clear and everybody understands roughly what we were doing. If you do have any questions, let me know.